So for the last two examples, I want to go over how to actually go through, and these are going to be general examples of integrating over non-rectangular regions. We've seen a number of different rectangular region integrals, and now we want to do the double integral over non-rectangular regions. And the way that I'm going to introduce this is through a problem that hopefully everyone knows the answer to, and that's the problem of exactly, showing, maybe you don't know the actual proof, but that you probably know the answer to it, which is, what is the area of a circle? And the second question is the more interesting question: how do we get that formula for the area of the circle? And hopefully you've seen already once, maybe at some point, in a relatively lower geometry class, you might have memorized that the area of a circle is exactly pi times the radius of the circle squared. It turns out that using our definition of area from the double integral, we can directly go through and actually derive this exactly. So we'll draw a picture first just to ground ourselves. And the idea is that you can immediately see that when you draw a circle, this is definitely a non-rectangular region, because of that, the function in the top and the function in the bottom, right, are not rectangles. So if our circle has a radius of r, we want to be able to go through and figure out what the area of this region is. So you'll recall from before that we defined the area of any region to be the double integral over that region of the constant function 1. So the trick is that we have to figure out correctly what the bounds of integration are going to be for this region. And you always want to remember the rule of thumb to start with the outermost bound first. In this case, we'll start with x, and then move to the innermost bound y. Well, the outermost bound x is going from this x value right here, which is negative r, to this x value right here, which is positive r. So very often, figuring out the x bounds is very, very straightforward. You can almost look at a picture sometimes and tell what the correct x bounds of integration is going to be. So x, right, is between negative r and r. Y, on the other hand, is not so straightforward because of the fact that for any given x value, if you fix an x value in this region, the lower bound for x is this, the bottom of the circle, and the upper bound for the lower bound for y is the bottom of the circle, and the upper bound for y is the top of the circle. And this changes depending on what point you look at, right? If we look at this point right here, it's going to have a different lower bound and a different upper bound than this point right here. So we have to include that in the bounds of integration for y when we figure this out. So what this means is that we have to figure out exactly how y depends on x for the upper and lower part of this boundary. And that comes directly from the equation of the circle, which is that x squared plus y squared is equal to r squared, which give us the equation r squared, or y squared is equal to r squared minus x squared, or y is equal to plus or minus the square root of r squared minus x squared. So for x between negative r and r, y is between positive the square root of r squared minus x squared and negative the square root of r squared minus x squared. And so our boundary for y here is going to be negative square root of r squared minus x squared to positive square root of r squared minus x. And you see that the upper and lower bound for a non-rectangular region in general will have to be a function. In general, you're going from the lower bound as a function of your first variable to an upper bound which is also a function of your first variable. But this is the correct way of doing this, and you always have to do this for a non-rectangular region. And this is why Fubini's theorem, which we'll talk about next lecture, is simple to state for rectangular regions, but sometimes can be very difficult for non-rectangular regions. So negative r to r, the antiderivative of 1 is just the function y. We have to evaluate this at the upper bound and the lower bound. So r or y evaluated at this upper bound is the square root of r squared minus x squared, and minus y evaluated at the lower bound. It'll be negative square root of r squared minus x squared. So the integral that we have to evaluate is the integral from negative r to r of 2 times the square root of r squared minus x squared. And this integral we can evaluate directly using the method from Calc 2 of trigonometric substitution. Specifically, we'll substitute in x is equal to r cosine theta, which means that dx is equal to negative r sine theta d theta. So this integral becomes the integral of the square root of r squared minus x squared, which in terms of theta is r squared cosine squared theta, and then dx is negative r sine theta d theta. And we also have new bounds from the trigonometric substitution. Our initial bound or top bound here is r, so when x is equal to r, you get the equation r is equal to r cosine theta, or cosine theta is equal to 1, which means that theta is equal to 0. And from a similar calculation, when x is equal to negative r, you get theta is equal to pi, because that means cosine theta is equal to negative 1. So the new bounds in this trig substitution are going to be from pi to 0. And then here we can factor out an r squared under the square root. The square root of r squared So we'll write this down. This will be 2 times, we'll move this over a little bit so we have a little bit more space. That's going to be the negative sign. It's negative 2 times the integral from pi to 0 of the square root of r squared times the square root of 1 minus cosine squared of theta times sine of theta d theta times r. There's an r right here as well. So the square root of r squared is just equal to r. We can also do this nice thing where you have a negative sign here, and whenever you multiply a definite integral by a negative number, the order of integration switches and the negative sign goes away. So this becomes 2 times r squared times the integral from 0 to pi of the square root of 1 minus cosine squared, which is sine squared, times sine of theta d theta. And then the last argument here is that sine of theta is positive when theta is between pi and 0. And so therefore this square root of sine squared theta is just equal to sine of theta. So square root of sine squared when sine of theta is positive is just going to be sine of theta. So it's sine of theta times sine of theta, or sine squared theta. And this becomes a nice trigonometric integral that we can go through and calculate. And to calculate this, we will use the double angle identity from trigonometry. Specifically, this is the double angle identity for sine squared. And this says that sine squared of theta is equal to 1 minus cosine of 2 theta divided by 2. So if we substitute this in integral, we have that 2r squared. This integral is 2r squared times the integral from 0 to pi of 1 minus cosine of 2 theta over 2. This is the integral with respect to theta. The 1/2 comes out, so the 2's cancel one another. So this is r squared, and the antiderivative of 1 minus cosine of 2 theta will be theta minus 1/2 sine of 2 theta. And this has to be evaluated from pi to 0. So our answer is r squared times pi minus 1/2 sine of 2 pi minus 0 minus 1/2 sine of 0. And sine of 2 pi is 0, and sine of 0 is also 0. So our answer is pi times r squared, which is exactly the area of a circle of radius r. This is really neat. That being said, you see that doing this in Cartesian coordinates is a little bit long, but it is possible to do, which is why I showed it. And Now, this is going to really emphasize when we get to polar coordinates, and specifically integrating in polar coordinates. It's going to emphasize how quickly, right, we can kind of increase the speed of these calculations and the ease of these calculations using the correct coordinate system. But that doesn't mean that we can't go through and do this for even for Cartesian coordinates if we want to. So for my next example, what I'll do is go through and show you how to compute the accumulation of the function f of x y is equal to x times sine of y. This is just the double integral of this function over the region R, where R is the triangle between the points, say bounded by the points. Zero, zero, pi 0, and pi pi. And you always want to kind of look at these first by drawing a picture of the region to get some sort of idea of what the bounds are going to be for the integral. So the point 0, 0 is right here at the origin. The point pi 0 is right here. 3.14159, the x coordinate, and 0 for the y coordinate. And pi pi is this point right here. And so the triangle bounded by these points is exactly this triangle right here, which gives our region R to be this region right here. And we're looking for the accumulation of this function, so it's a double integral of this function over this region R. Now, to set up the bounds here, start by just writing down our general expression for the accumulation, which is going to be the double integral of the function x times sine of y dA and you can choose either order, but I'm going to use x first because in the next lecture I'll show you how to correctly switch the order of integration for general regions. It's a little bit more complicated for general non-rectangular regions than it is for rectangular regions, but this is a topic of Fubini's theorem, and I'll discuss this at length in the next lecture. for now, we'll just focus on what we know, which is that if we start with x, our x bound is going from 0 to pi, and the outer bound is always going to be a constant to a constant. So we're going from here in x to here in x. And then as we go from 0 to pi in x, our y bound is going from a lower bound of here to an upper bound of here. So the lower bound for y will be 0. The upper bound for y will be this curve right here, which doesn't take much to figure out exactly what this curve is. It's the line of slope 1 from this point to this point, for the curve y equals x. So our y bound will be from 0 to x. And we've effectively set up our integral. Be careful here, it's not from 0 to pi. If you do from 0 to pi and 0 to pi, you're going to get the integral of this function over the entire square here, right? Which is not what we want. We do not want any of this region to be included in the accumulation. So if you just do pi here, you're going to get the wrong answer. And that could be very costly if you're, say, calculating some sort of physical property using this double integral, because you're going to get the wrong answer, and that's going to negatively affect whatever application you're doing. But this integral as written is the correct form. We can simplify this by factoring out the x here, because it does not depend on y at all. This is the integral from 0 to pi of x times the integral from 0 to x of sine of y dy. This is our inner iterated integral. And the integral of sine of y is going to be negative cosine of y. This is going to be integral from 0 to pi of x times negative cosine of y evaluated from x to 0. Or when you plug in the bounds, this is x times cosine of 0, which is 1, but you're subtracting that, so you get positive 1 right here. You get minus cosine of x. And then this is going to split into two separate integrals. The integral from 0 to pi of x dx minus the integral from 0 to pi of x times cosine of x dx. This first definite integral is going to be x squared over 2 from pi to 0. And the second iterated integral can be done using integration by parts, where our u is x, our dv is cosine of x dx, our v then will be equal to sine of x, and our du will be 1 dx. From the integration by parts formula, this will be u times v, which is x times sine of x, evaluated from pi to 0, minus the integral of v du from 0 to pi, which is just going to be the integral of sine of x dx. This is the v du term in the integration by parts formula. Remember this from your Calculus 2 class. And sine of pi is 0. Sine of 0 is 0. So this entire term right here is 0 when you plug in. This entire term right here is just going to be pi squared over 2 minus 0 squared over 2. So this is going to be pi squared over 2. And this negative times negative is positive. So you have your pi squared over 2 plus the integral of sine of x, which is going to be negative cosine of x from pi to 0. Or pi squared over 2 plus 1 minus cosine of pi. And cosine of pi is negative 1. This is 1 minus negative 1, which is 1 plus 1, or 2. Final answer is 2 plus pi squared over 2. This is the value of this double integral, which is the accumulation of the function x times sine of x, or x times sine of y, over this triangular region. So this is pretty neat. This value is the exact value of the net volume under the graph of this function. Remember that we say net volume because we mean the total amount of positive volume of the function, the graph of the function above the xy plane, minus the total amount of volume below the xy plane. The next application that I want to talk about is computing the volume enclosed by two surfaces, an upper surface and a lower surface, or a top surface and a bottom surface. So suppose that we have two separate surfaces, a top surface, I'll call it surface 1, where z is equal to some function I'll call z top of x and y, in surface 2, which I'll call z is equal to the function z bottom, or z bot of xy. And we're assuming here that z top is always greater than or equal to z bot, or z bottom, for all points x and y in some region R. You know that the integral of any function is the, if it's positive, is the volume underneath that function. Well, that means that because z top is always greater than or equal to z bottom, that z top minus z bottom will always be a positive function, and it doesn't take much, so it's not too difficult to see that the volume between two surfaces, z top and z bottom, is going to be the double integral of z top minus z bottom. Similar to how if you have two separate functions, one that's greater than the other one, the area bounded between those two functions is the single variable integral of the top function minus the bottom function. Sometimes say is the volume bounded by the two surfaces, so the volume between the surfaces one and 2, this is going to be directly equal to the double integral over r of z top minus z bottom over the region R. So for an example of this, let's go through and directly calculate the volume of a sphere of radius A. And this can be done by first drawing a picture. We always want to start by drawing a picture and getting an idea of what our region R is that we're going to be integrating over. So the sphere of radius A is given by x squared plus y squared plus z squared is equal to a squared, or z squared is equal to a squared minus x squared plus y squared. When we solve this equation for z, we get that z is equal to plus or minus the square root of a squared minus x squared minus y squared. And this gives us directly z top is when z is positive. This is the positive square root of a squared minus x squared minus y squared. And z bottom is equal to negative the square root of a squared minus x squared minus y squared. So you see I've done all of this without drawing a picture, but the idea is that this very clearly gives us right, the picture that we're looking for in the equations that we're looking for when we want to go through and integrate this. So in general, when figuring out this region R, you want to think of what the traces of this, the thing that you're looking at to figure out the volume are, or what the traces kind of look like in the traces of this equation. Specifically, this equation is going to have a maximum trace when z is equal to 0, which is just a circle of radius A. So when z equals 0, the trace is x squared plus y squared is equal to a squared, or a circle of radius A. Which is going to look like this. In general, you want to think of what this looks like as you're looking down on the z-plane. And z top is going to be the top of this sphere. Then z bottom will be the bottom of the sphere. This is the top of xy. and this is the bottom of xy. So the integral that we're going to get to figure out the volume of this region is going to be the double integral over the region R of z top, which is the square root of a squared minus x squared plus y squared, minus negative the square root of a squared minus x squared plus y squared. Which is a direct application of the formula that I just wrote down. And if we go through and simplify this a little bit, this is going to simplify nicely to 2 times the square root of a squared minus x squared plus y squared, or the double integral, 2 times the double integral over r of the square root of a squared minus x squared minus y squared. And this is equivalent to saying that the volume of the sphere is 2 times the volume just under the hemisphere, top hemisphere, above the xy plane. So this integral can be set up and directly evaluated. We're integrating over the circle of radius a. So if you think of what this cross section is, the bounds are actually going to be the same as the bound from the previous problem. And you can see that very quickly by just kind of drawing down the region R, which is the circle, x squared plus y squared, all points x and y inside the circle of radius, not 1, but a squared. So our x bounds are going to be from negative a to a, and our y bounds are going to be from the bottom curve here to the top curve. The bottom curve is given by y equals negative the square root of a squared minus x squared, and the top curve is given by y is equal to the square root of a squared minus x squared. So the bounds of integration are going to be in x from negative a to a, and in y from negative the square root of a squared minus x squared to positive square root of a squared minus x squared. I'll add in a little bit of space here so that things don't look too compressed. So this calculation, just like before, is directly possible to do using Cartesian coordinates, but it's a little bit long. So I'm just going to briefly describe how to do that here, and I'll actually go through and directly do it all out in the lecture slides that I'll post to our course page. So just so you can see that it is in fact possible to do. But it turns out that it'll be much easier to do, almost orders of magnitude easier to do when we look at it in spherical polar coordinates. Once we learn how to do integration in spherical polar coordinates, It's also much easier to do in cylindrical coordinates as well. But the easiest coordinate system to use here is the sphere, and that's going to involve the triple integral. So I'll revisit this a little bit later when we get to that. But in order to go through and do this in Cartesian coordinates, you first have to do a proper U substitution. And because we've chosen y as our iterated integral, this is going to be a proper substitution for y. So remember here, when we're evaluating the integral, we start with the iterated integral right here. So the proper substitution here can be a little bit confusing at first if you're looking at this, but this can be done with the trigonometric substitution. Specifically, if we substitute in y is equal to the square root of a squared minus x squared times sine of theta, which will then mean that dy is equal to the square root of a squared minus x squared times cosine of theta d theta. This integral will be able to go through and evaluate it. Specifically, what we will get is that this is equal to, this is the volume, remember, 2 times the integral from negative a to a times the integral from negative pi over 2 to pi over 2 of the square root of a squared minus x squared times the square root of 1 minus sine squared times and in parentheses square root of a squared minus x squared times cosine theta d theta. dx. So it's a little bit longer. However, you notice that this is the same thing as 2 times the integral from negative a to a square root of a squared minus x squared times square root of a squared minus x squared give us a squared minus x squared, which comes out of this integral because this is a theta integral right here. 1 minus sine squared is cosine squared. This is the integral then negative pi over 2 to pi over 2 of the square root of cosine squared theta times cosine theta d theta. And remember, we're really just focusing on doing this inner iterated integral first. You always start on the inside, and when you're evaluating, you start at the inside, and then you kind of work your way outwards. When you're determining the bounds, you work in the reverse direction, which I explained earlier. But this simplifies to then cosine squared of theta under this integrand, and using the half angle formula again, only this is going to be the half angle formula for cosine squared. Yeah, cosine squared of theta is equal to 1 plus cosine 2 theta over 2. you'll be able to go through and solve this inner integral, then solve the outer integral. And what ends up happening is this directly reduces to 4/3 times pi times a cubed. So I'm going to have you fill in the blanks here. It's good practice to go through and fill in the blanks here. However, the solution is in the slides posted on the course website. So you can go through and take a look at those if you get stuck filling in the blanks. But it's a really good exercise to kind of finish this. And I know that it's a little bit long, right? Because we're not using the best coordinate system here. We're using Cartesian coordinates or rectangular coordinates when we're trying to compute, right, an integral that is in a place of symmetry, having symmetry that is not rectangular at all. So there are better coordinate systems to use here, which is why this is taking so long, and it takes so long. But it is actually incredible that we can go through and still get the exact integral here, the exact value for the formula for the volume, even in Cartesian coordinates. But we'll see a little bit later on that this process is going to be simplified exponentially as we move on into actually integrating in new coordinate systems.